Well, first of all, thank you very much for having me. And today I'm going to tell you about peer effects. So we know that peers matter for student outcomes. So who your classmates are matters for your test scores. Another thing we know, however, is that a widely used model, the linear means model, doesn't seem to be an appropriate model to capture peer effects. So this is ability peer effects. So this is a model where your own test scores are a linear function of the mean ability of your peers. Doesn't seem to capture peer effects that well. We don't really know why. So related to this, we don't know how they work. So for example, if we see that when we put good classmates together with other people do well, is it because we learn from good classmates? Or is it because maybe we're encouraged to keep up with them because they're good, we want to be like them? We don't know what the mechanism is. And why do we care? We care because they have different implications. Different mechanisms have different implications for policy. So for example, if we always learn from good classmates no matter what, then we will want to spread them across as many classrooms as possible, really high ability people. But now suppose that it's more a story of, oh, I'm encouraged to keep up with them, then maybe it also matters how far I am from a very bright person, because if I'm very low ability, I might actually get discouraged. So when you try to do like out of sample predictions, you might fail. And that's actually a point that was made in an important paper in the peer effect literature that was published on Econometric. That's Carol Sacerdot and West. And it casts doubt on whether we can use existing evidence, which is mainly reduced form ability peer effect evidence, to improve classroom organization. So if I think of the contribution of my paper, it's actually trying to open up a little bit this box and trying to understand what's generating peer effects. So my approach is that I'm going to develop a model, a theoretical model of social interactions that has implications on the shape of ability peer effects. And the model I have in mind is one of rank concerns. So it's the idea that maybe students, they're competing with each other because they care about the rank in the class in terms of test scores. So another contribution of this paper is that I'm going to propose a new way to identify heterogeneous and nonlinear peer effects. In fact, from the literature, we have evidence that, if anything, ability peer effects tend to be nonlinear and heterogeneous. And I'm going to estimate them among Chilean 8th graders. And finally, I'm going to use the empirical findings to formally test the theoretical predictions of the model. And I'm going to use the Chilean 2010 earthquake as a natural experiment to do this. So let me just give you quickly an idea of why rank concerns might generate peer effects. So when peer effects are generated by rank concerns, they're going to operate through the entire ability distribution, not just the mean. So imagine that you care about your rank in a class. So it really matters how much better than you the person next up in the ability distribution is. Because if they're similar to you, then you know that if you put in effort, you might surpass them. But if they're a lot better than you, then maybe you give up because it would be too costly to surpass them. And you see how this reasoning is true for everybody in the ability distribution. So it's the entire distribution that matters, not just the mean. I'm going to focus on the variance. So basically, the goal here is, well, I want to compare distributions of abilities, and they're two infinite dimensional objects. So a way to simplify the problem is, let's just look at classrooms that are different in terms of variance. It's simple enough, but it's also complex enough as a comparison, because if you keep everything constant about a distribution and you just change your variance, you're going to change the density differently in different portions of the distribution, and that is something that allows me to derive some interesting theoretical results that I can then test in a simple way. One of the results of the theory is that the effect of increasing the variance of ability in a classroom, if there are rank concerns, is that it is heterogeneous. And some students are going to benefit from it, and some students are going to be hurt by it, depending on their ability level. So when I go to the data, I need to be able to capture the heterogeneous effect of changing the variance of ability. So what I need, pretty obviously, for identification, I'm going to need some exogenous variation in the ability variance. For that, I'm going to use the earthquake. And for estimation, I need an econometric model that allows me to detect any patterns of heterogeneity across the ability distribution. And for that, I'm going to use some semi-parametric techniques. Just very quickly, preview of the results. I do find supports of rank concerns, or I would not be here. I think there are important implications to my findings for policy. Basically, I have uncovered a new channel of operation of ability tracking. So this is the idea of putting students of the same ability together. Common wisdom is it must be bad for the low ability students, but then when you go to the data and the few papers that have actual randomized controlled trials of ability tracking, they find that they work for everybody. Well, actually my paper says one of the implications of having rank concerns is that it's going to be easier to compete among equals, so you actually would not be too surprised to find that ability tracking works at all ability levels. If it is true that there are rank concerns and that is one of the channels through which peer effects are generated, then that means that educators can exploit these incentives. It means that if you reallocate students across classrooms, you're going to generate incentives that you can try to exploit as a social planner. There's also implications for the estimation of peer effects. So the models that focus only on the mean, and I have to say the literature is moving away from these models because there is a consensus that they're not the best. But they may fail in out-of-sample predictions, and we have seen that happening. They might even fail to detect peer effects when these are present, because these models typically look for a certain clustering of outcomes within a group. Rank concerns are going to generate peer effects, but they're not generating outcome clustering, so you might miss them, even if they exist. So I will start with the empirical part, and I will go to the model at the very end. So in terms of data, what I do, I combine 4 waves of the SIMSE data set. The SIMSE is an administrative data set with information on the universe of students. In particular, I will have 8th and 4th grade math and Spanish test scores. And I create 2 cohorts of students. One, I will call it the pre-earthquake cohort, because they're observed in the 4th grade in 2005 and in the 8th grade in 2009. The second one, I call it post-earthquake cohort, because they're affected by the earthquake that happened in 2010. My outcome of interest is 8th grade test scores. I see household characteristics, I see teacher characteristics, I see classroom characteristics. What is a very desirable feature of my data set is that I have identifiers that match students to classrooms, therefore to their classmates, to teachers and to schools. So this is what makes this data set ideal for the study of peer effects down to the classroom level. The earthquake happened in 2010, it was very strong. The SIMSE 2011 sample was collected 20 to 22 months after the earthquake happened, and at that point, the vast majority of repair hadn't happened yet. So people were still suffering from disruptions. 80% of the population was affected, but people were affected differently. They were not all affected in the same way. So if I go to my data set and I look at the damages to the homes of the students in my data set, I see that they actually varied from $20, which is about 4% of the average household income in my sample, to over almost $14,000. Now, parents and households didn't have to pay this cost. They were all covered by the government. But this is just to give you an idea. There was a lot of variance in the damages to student homes. And if I actually look, of course, there's very few people who were hit that badly. So if I look at the distribution, the mode is about 220, so about half of household monthly income. So this is the distribution of seismic intensity in the students in my sample. So the first thing that I do as a preliminary data analysis, I say, well, does it matter for test scores to be affected by an earthquake? So I exploit the fact that I have a pre-earthquake cohort and a post-earthquake cohort, and then I have earthquake regions and non-earthquake regions. And then for each student, I observe test scores at 2 points in time to do a very simple diff-in-diff regression with test score value added. And this regression is telling me that being exposed to the earthquake reduced test scores by 5% of a standard deviation. The second question I ask is, well, does the actual extent of damage to your home matter? Because we've seen people were affected differently. And the answer is yes. And I compute that for every extra $100 US in damages, test scores reduced by 1.6% of a standard deviation. So that 5% is actually an average. So why is that the case? Well, one possible explanation is that damage might reduce the ability to study. And I do have some evidence about that. For example, students that were affected more badly actually report that it's harder for them to study. So a key feature of my data set is that I actually see that there are large differences in damages even within classmates. People who are sitting in the same class were affected differently. Now, there's a tiny caveat about this. This home damage measure, I can only measure home damage at the town level. So it's an expected, so if you live in a certain town, it's expected that the damage to your home is this much. So that means that these differences in damages between classrooms, I can only pick them up in classrooms that don't have students all coming from the same town. And about half of all the classrooms in my sample satisfy that condition. So my data set has over 100,000 students and over 3,000 classrooms. So if I look at these classrooms, which are those that I then keep in my data set, in my sample, the average standard deviation in damages is really large. It's $350 US, and there's also variation across classrooms, which is 92% of the average household income. So why did I show you this? Let me tell you what the identification idea, therefore, is. So we know that different classrooms have different damage distributions. And we know that damage, at least it is reasonable to think that damage reduces your ability to study. So for a second, don't think about ability simply as your IQ. Think of ability as something that's affected by various characteristics of a student. Then, if that's the case, then, and if damage affects your ability to study, then classrooms that have different distribution of damages have different distributions of ability to study. And crucially, this variation, so if I look at classrooms with different variance distributions, distributions of damages, this variation is free of the typical confounding factors that you would encounter if you compare classrooms that have different distributions in any other component of ability. So if we look at classrooms that have different distributions in initial test scores or parental education, we know that that variation carries a lot of confounding factors. But I will convince you that I'll try to convince you that that's not the case when you look at classrooms with different distributions of damages. Just to give you an idea, this is the type of data variation that I use. So each point here is a school. In fact, I have data down to the classroom level, but it was complicated to show it in a graph. So each point is a school. These are schools where not all students come from the same town. So there's a positive variance of positive variance of damages. What I want you to notice is three things. One, there's a lot of dots, which is good. A lot of data points. Two, these dots have different sizes. Each size is a certain level of variance of seismic intensity. Three, you see dots of different sizes close to each other. So I will find schools that look very similar in a lot of ways, but they have different variance of damages. So the econometric model has to allow for home damage to affect own ability to study. And then it will be an empirical question whether that's the case or not, but at least it has to allow it. There have to be direct peer effects, which is what I'm after. By direct peer effect, I mean it's a peer effect generated by peer-to-peer contacts or interactions. So that means that student outcomes have to depend on classroom distribution of ability to study. So that's my definition of a direct peer effect. But I want the model to be as general as possible. So I want to have it the elements that normally you want to get rid of when you want to really estimate just the direct peer effect. So I will allow the model to have also indirect peer effect. So that is the fact that when you change a composition of students, other things about the classroom might change. For example, teachers might teach differently. So it is a peer effect, but it's indirect. It's mediated through the teacher. And then correlated effect. Here I'm following Mansky's terminology. So I let the model have this correlated effect. The idea here is that the effect of an observed classroom characteristic might depend on classroom composition. So when you look at classrooms with different classroom compositions, they kick in and they confound your direct peer effect estimates. Moreover, as I said earlier, I'm really interested in estimating heterogeneous peer effects. So I will allow to have the model as general as possible. I will allow all three of these effects to be heterogeneous. So they will vary by a student's ability to study. And then what I'll do, I'll make assumptions that will allow me to separately identify direct peer effect from indirect peer effect and from correlated effect. And hopefully I'll convince you the assumptions are reasonable. So this is the econometric model. This is the achievement production function with peer effects. So y is test score of student I in classroom L. It's going to be a function of a student's type. So I've been talking about ability to study. That's what the type is. I will actually model it as a cost of effort. It will be clear in a second why. So the cost has the opposite effect of the ability to study, obviously. So I'm going to talk interchangeably about ability to study and cost of effort. And what is a student's type? It's going to be a function, a linear function of all the things I see about the student that I think affect their ability to study. So this will have initial test scores, parental education, parental income, and gender, I think. So why are there direct peer effects? Well, if you look at this function, it depends on the classroom distribution. So that's what's generating a direct peer effect. There is an indirect peer effect because ZL are classroom characteristics, and their effect not only varies by student type, but it also varies by the composition of students in the classroom. So that's a distribution of the student X's in classroom L. And finally, there are correlated effects, because if you take the expectation of this thing, the conditional expectation is different from 0, and I actually model it, and it's going to be a function of student type, classroom characteristics, and the distribution of student characteristics. So this is student composition in the classroom. So the goal is that I want to estimate the effect of changing the variance of C, so the variance of the cost of effort or the variance of the ability to study, on E, on this function E, net of its effect on indirect peer effect and correlated effect. One thing I want to say here, that 3 of them are additively separable. In fact, I only need E to be additively separable from U and phi, but for exposition here, they're all additively separable. So what is the problem here? That when you change the variance of C, you're also changing the variance of the x's, because C is determined by the x's. So when you change the variance of C, also indirect peer effect U and correlated effect C are going to change. So what is the solution? The solution here is, well, find a determinant of the cost of effort of a student that it's not in X, so it's not one of the student characteristics. Its classroom variance is going to affect the variance of the ability to study, but not the variance of the student characteristics X. And therefore, it's not going to affect the indirect peer effect U and the correlated effect C. So what is this characteristic or this variable? Well, for students who are in the post-earthquake cohort, I assume that their cost of effort, I allow their cost of effort to be affected by the damage to their home, and I interacted with student characteristics. So that means that in the post-earthquake cohort, classrooms that have different variance of the, I should be more specific, this is variance of seismic intensity, they're going to have a different variance of the cost of effort. So that is going to generate direct peer effects. Clearly here, I'm obviously making an exclusion restriction, and the exclusion restriction is that indirect peer effect and correlated effect depend on the variance of the student characteristics, but they do not depend on the variance of seismic intensity or damages. Is that a reasonable restriction? That's what I hope I'll convince you it's a reasonable restriction. Well, can I check if it's a reasonable restriction? To answer that question, let's first see what it is that I can identify. So to remind you, this is the model. The U, the indirect peer effect U and correlated effect C are classroom specific, so there's an L here. But also this function is classroom specific because it depends on the distribution of the C in the classroom. So I cannot really hope to separately identify these 3. So all I can identify is this M function. And just to remind you what C is determined by student characteristics, and for students in the post-earthquake cohort, that's what PI equal to 1, it's also affected by the damage at their home. So this is a standard semi-parametric single index model. You just normalize one element of alpha, and then I jointly estimate alpha and M. By the way, it turns out damage does increase the cost of effort according to the estimates. So that means I can only identify this M function. I cannot directly check whether U and C vary with variance of seismic intensity, because I cannot separately identify them from U. So what do I do to check whether my exclusion restriction is reasonable? I say, well, do I see any correlation between the variance of seismic intensity and variables that typically generate indirect peer effect and correlated effects. So what I do, I check in the data if there is any correlation between the variance of seismic intensity in a classroom and observed classroom characteristics, like, for example, who the teachers are, because it would be problematic if, for example, I don't know, schools decided to assign better teachers to classrooms that had a larger variance in damages. That would create a kind of indirect peer effect that would be problematic for me. Is variance of seismic intensity correlated with student characteristics? That would indicate that maybe there's a resorting of parents, certain parents avoided classrooms that had larger variance in damages. That would be problematic for me. Or do I see a correlation between variance of seismic intensity and observed teacher effectiveness? That would generate indirect peer effect. Here, my measure of teacher effectiveness is how much of the curriculum teachers were able to cover. Clearly, if the answer was yes to any of this, I would be in trouble. I'm like, no, I don't like that answer. So what's the bad news? That the answer is yes, you do see a correlation between the variance of seismic intensity and these variables. But what is the good news? The good news is that that is not the effect of the variance of damages. That's really a spurious correlation. Because if I go to the pre-earthquake cohort when the earthquake hasn't happened yet, and I build a measure of variance of seismic intensity in each classroom, I can do it, because variance of seismic intensity is based on a location. But clearly here, the larger the geographical dispersion of the students in the class, the larger the variance of seismic intensity mechanically. And classrooms that have larger geographic dispersion, guess what? Students get better test scores. They're better classrooms. They attract people from far away. Probably they have different characteristics. The students are more motivated. So there is a correlation, but this correlation is constant in the pre-earthquake and in the post-earthquake cohort. It's the same. So what that is telling me is that any correlation is really spurious, and I don't have to worry that there's actually an endogenous reaction to the variance in damages. So that means that I can account for any correlation by differencing it out. So just to give you an idea of what it is, rather than putting up equations, I just prepared this graph for you. So imagine that I have two identical classrooms in the pre-earthquake cohort. I call them L and L prime, and two identical classrooms in the post-earthquake cohort. I call them S and S prime. By identical, I mean they have the same distribution of student characteristics, the same teacher characteristics, the same classroom characteristics. So identical on a high-dimensional object. So imagine I can find these four classrooms. So in the pre-earthquake cohort, if I just look at the pre-earthquake cohort and I plot the M functions that include the E function that I'm interested in and the other confounding functions. So if I plot them, so this is C, and that's predicted test score. Any difference between these two is only due to these geographic dispersion effects that are, you can call them spurious, but they're not what I'm after. This is potentially confounding. But then if I go to the post-earthquake cohort and I take a difference between these functions, this difference is going to have the geographic dispersion effect and the direct peer effect, because here it's not only the variance of seismic intensity, which is a geographic measure of dispersion, also the earthquake has happened here. So these classrooms have different variance of damages, so they have different variance of ability to study, so they're going to have the direct peer effect in here. Now you can see where I'm going. So here you see how, by the way, how I'm doing point-by-point differences, so I can capture any heterogeneity of these functions. Any heterogeneity of the effect with respect to C. So you can see where I'm going. If I put the two functions in the same graph, you take the difference, you're left with the direct peer effect. And this is a difference in differences. I don't really have time to stress the subtlety of an advantage of this method over, for example, quantile diff in diff, but I'd be happy to talk about it if you're interested later on. Of course, the data don't look as nice. That's never the case. In the data, I don't have 2 and 2, 2 classrooms in the pre, 2 classrooms in the 4 that are identical, blah, blah, blah. You don't have that. So what you have is this mess of a lot of classrooms before and after the earthquake. So what I have to find all possible pairs of classrooms that satisfy 2 conditions. They have to be identical along many dimensions, except for the seismic intensity variance. They have to be subject to the same treatment intensity. So here I just told you, really what I'm after is what's the effect of increasing the variance. I don't really care about the amount, because to test the model I don't need that. But clearly, when I make the comparisons, for the comparisons to make sense before and after, so when I put the two functions in the same graph, you need the treatment intensity to be the same. So what I do, therefore, when I actually implement this, I'm going to perform all possible pairwise comparisons. I consider the classroom with the larger variance as the treated one. When there are n classrooms, there's many comparisons. And then I have to control for a high-dimensional vector, so I'm going to use kernel weighting, kernel matching, because there's not many classrooms that are exactly identical. Same thing, I build kernel weights for the intensity. So at the end, what I'll do, I will build a weight for a quadruplet, for a pair of pairs of classrooms. And then, once you do that, you can elegantly represent the estimator I'm after at each point C. So that's the effect on test score of increasing the variance of damages at a point C. So this is a level of student ability. So you can represent it as a weighted regression on a constant. And then you do this, basically you take this difference in differences at each point C, then you weight it with the weight that I've built, and then you loop over all classrooms, and you do it for a grid of values of the cost of effort of the students. And in the end, and of course you can't use data for this. And in the end, what you're left with is a beautiful graph. I thought it was beautiful. So what this is telling me is, okay, this is the cost of effort of the student. Here, what I'm plotting on the y-axis is what is the effect on test scores of increasing the variance of the cost of effort or of the ability to study. And this is really, if you believe what I told you, this is the causal effect. I got rid of all confounding problems. What this is telling me is that the effect for people in the middle, it's negative. For people at the top of the cost, so these are low ability students, it's positive, but really it's not really different from zero, or it could be positive or negative. And this is math test scores. So math test scores, I'm like, okay, this is a pattern. What about Spanish test scores? It's a different pattern. Spanish test scores, for people low middle cost, the effect is negative of increasing the variance of ability in the classroom. But for high cost, low ability students, it's positive. This one is not statistically positive, this one. So it stays below or it gets arbitrarily close to zero, but it doesn't go positive. So you might wonder, okay, what do those results mean? Which is what I wondered too. So the question is, what mechanism of social interactions can generate these patterns? They're kind of crazy and they're different between math and Spanish. Why is that? So why is that? I have an answer. The answer is, well, actually, it turns out the theoretical model can explain them in a very simple way. So the model is actually, it's not a contribution, a theoretical contribution. I don't want to claim it is, but it's actually an application of a theoretical paper on conspicuous consumption. So the assumptions here is, and I just adapt their model to the case of test score production. So the assumptions, some of them are very standard. So achievement is produced through costly effort. So this is effort of student I. This is a student type. It's like a parameter in the model. And this is the cost of effort. So really C is something that will increase the cost of effort for every effort level. So I will improperly refer to C as a student's cost of effort because it's something that increases their cost of effort. Then students are going to be heterogeneous in terms of this cost of effort. So there's a certain distribution in each classroom of the cost of effort. There are technological spillovers of the standard type, of the one that everybody has, many people have modeled. So the standard type means they work through mean of peer ability. In this case, it's the mean of the peer cost of effort. So that means if I'm in a classroom with a higher cost of effort, no matter what, you're going to get lower or positive or higher, but lower makes more sense. Lower test scores independently of rank. So it's an alternative mechanism, channel of peer effects. And utility is increasing in own achievement. So far, so good. These four assumptions have appeared in countless times in the literature. What is the novel assumption is that, well, what if utility is also increasing in your own rank in terms of achievement. So you really care about where you are in the achievement distribution. What is if that is the case? As I said, the first four are standard, the fifth one is not. Okay, so what does the achievement production function look like with technological spillovers? This is achievement of student I in classroom L. It depends on the level of effort that student of a certain ability or cost of effort I exerts. So this is going to depend of L because it's going to be an equilibrium object in the end that depends on the distribution of cost of effort in the classroom. So there is technological spillovers because the productivity of effort is going to depend on the mean cost of effort in the classroom. So this is a technological spillover. But also I let mean cost of effort in the classroom and other classroom characteristics also affect the level of achievement. So you see how there's this alternative channel of peer effects that works in two ways. Okay, so the utility is going to have two components. There's the utility from achievement, so from your absolute level of achievement, that depends also on the cost of producing it. And then there's the utility from rank. So the utility from rank, your rank is given by the fraction of people in the class who has a test score that's lower than your test score. So the overall utility is going to be the product of these two. When phi is equal to 0, this is going to generate what I call aversion to a low rank. That is because if you're the last person in class, you actually don't even enjoy utility from your own achievement in absolute level. So actually a nice thing about this model is that it is in a way unifying of previous evidence in the literature. So on one hand, okay, we do have evidence from the lab that people sometimes have aversion to a low rank, but actually what I show in a different paper is that this model, this special case of the model, when there is aversion to a low rank, so students, when they get close to the bottom of the distribution, they're desperate to get out of it. So this can explain all the results in the Econometric paper that I mentioned at the beginning. So that has some puzzling results. This one can explain all of them, and it can also explain further experimental evidence from University of Amsterdam students. The case of phi greater than 0, in that case, it's when there's no aversion to a low rank. In a way, it's a more like a linear preference for rank, where everybody cares about rank in the same way. This one can actually explain, you'll see it in a second, can explain the results from this paper. So I think that's kind of a nice feature. So students are going to maximize utility with respect to effort. I'm going to just focus on symmetric equilibria. So symmetric strategy is a mapping that goes from a student type to their effort. So if you stare at the first order conditions, one of the things you notice is that the larger the density around your type, so the more people there are who are like you, the larger your marginal utility of effort. That is because for the same cost of effort, you can surpass more people. Clearly. So that's one of the incentives at play. There's others, but I want to focus on this one because it will allow us to understand the results, the comparative static results. So I adapt the proofs in Hopkins and Kornienko, and basically they go through as in that paper. So you can show that there is a unique symmetric Nash equilibrium and that the equilibrium strategy is strictly decreasing in type. So the larger your cost, the lower your achievement. That actually, it's a consequence of some of the assumptions I make. So this is something that ideally I would also like to test, and I can do it. And the most important result is the comparative statics result, and that is that the effect of increasing the variance of C is heterogeneous across individuals. Of course, it depends on the phi, but I already told you we're in the phi greater than 0 case. So it depends it varies across individuals. Okay, so let me show you the comparative static result. Let's just focus on this one, because that's the case we're talking about today. This one can explain other results in the literature, but we're just focusing on this one. So on the y-axis, we have the effect of, on the x-axis, we have the cost of effort of the student. So high cost, low ability students, low cost, high ability students. On the y-axis, we have what is the effect on achievement of increasing the variance of C in the classroom. And you can see that it's either positive, negative, positive, or negative and then positive. You might remember these are exactly the two graphs I showed you earlier. One was a Spanish case, the other one was a math case. I told you, so suppose we're in a low variance classroom, the green one, and I move you to a high variance classroom, and everything else, support of the distributions is the same. So if I'm a high cost student, there are more people like me, so I have an incentive to work harder because the marginal utility of effort here is higher. So that explains why in both cases you see that test scores increase for these people. Now for people in the middle, there's two incentives. On one hand, there are less people like them, lower marginal utility of effort, they're gonna reduce their effort. On the other hand, these people are exerting more effort. So now you have an incentive to exert more effort yourself if you don't wanna, lose rank. But there are gonna be people, so you can show theoretical, the further away you move from the top of the distribution, you're gonna hit a point where people are gonna reduce their effort. So that explains why we see people in the middle doing worse. And now here we saw opposite things for math and Spanish. And that's because here again, there's two opposite incentives. On one hand, if you move to the high variance classroom, there's more people like you exert more effort. But on the other hand, people below you are resting on their laurels, so you can also do the same and you won't reduce your achievement. So basically here, what you do depends on how much you care about your rank relative to absolute level of achievement. And what we see is in the data is consistent with math students caring more about competition and rank, and Spanish caring more about absolute level of achievement. So I don't have time to go through this, but I said I can at least test monotonicity. Let me just say I used Dennis's paper to test monotonicity of M, which is not the same thing as testing monotonicity of E, which is really what I'm after, but at least it's nice that I see that M is monotone decreasing. I do not reject the comparative static results. I showed you the graph look the same. Like the theoretical predictions are the same as the empirical finding. So the nice thing about having a model, you might wonder, why do you do the model? Isn't it not enough? I got this many times. Is it not enough to just look at the empirical? Well, I can do out-of-sample predictions in this case. So given the type of rank concerns I find evidence for, I can tell you that if there's, if we track students by ability, now tracking students by ability is an out-of-sample type of variation, because in the data, the type of variation I see in the data is you keep the support of a distribution constant and you change the variance. Tracking, you are partitioning the support of the distribution, so it's a different type of data variation. But using the model, I can tell you, well, given the type of preferences for rank concerns, if you were to do tracking, everybody would have an increased incentive to compete and to exert more effort. So, so this is a type of out of sample predictions that you can do only because you have the model. And tracking is a really important peer reallocation policy. I won't talk about the alternative mechanism. Just trust me that I've thought about alternative mechanisms and I've ruled them out. There's one that I cannot rule out, however, because all I can see really in the data, if you believe that I have this exogenous variation, basically all I have is an exogenous variation in the variance of ability, and I estimate the heterogeneous effect that that has. And then I give an interpretation through the model to that variation. So I can't really, it could be a technological spillover of another kind. And to actually tease apart a different mechanism, you need a different type of data variation that all I'll tell you is that I'm actually working on it. So you basically, ideally, you would like two different types of data variation. One where you just change a composition, one where you change the merit incentives and the incentives to compete. And one of the results of the paper is actually these two types of policy interventions that have always been studied separately. There could be an interaction between the two. And now I'm working with the Ministry of Education in Chile to try to generate a randomized trial that will allow me to do that. Thank you.
Thank you very much.
Well, thanks for organizing this. I think this kind of conference is a brilliant idea, and it's intergenerational interactions as well as interaction between theory and empirics. I'm not one person who needs to be convinced that you need a model to interpret these results. Actually, part of my discussion will be exactly about that link. Let me start by saying this really creative paper. I think that the peer effects literature needs much more systematic work of this kind, where theory is brought together with empirics. I think it's intuitively clear to me that averages, in some sense, don't matter, are not the first order thing. For example, even in a relatively small school, people will allocate themselves to subgroups, and they will, there might be some kind of sorting. There are all sorts of reasons why averages of performance may not be the main dimension that you want to look at. And Michela here looks at a kind of different kind of idea that, which is a very intuitive idea, that people actually care about rank. So the aim of the paper is to develop a model of peer effects and scholastic achievement, and to understand how the variance of student performance matters for outcomes. The variance being, of course, as Michela stressed, a shortcut to the kind of the entire rank distribution of the classroom. And the paper is not structured like the presentation. It starts with a model, and of course, what's important about the model is that it actually solves out for equilibrium. It kind of asks, well, what's the equilibrium level of effort in a classroom, given that there are rank concerns? And then the theory is analyzed on the basis of implicitly of varying this equilibrium as costs of effort change. Okay, so why is this important? Well, when you talk about policy, one of the big things that people talk about is about tracking. So how do you allocate students in classrooms? Does it matter do you want very heterogeneous classrooms? Do you want very homogeneous classrooms? This kind of paper says, just to preempt, maybe. It's not so much the heterogeneity or the homogeneity, but you want some heterogeneity, but you also kind of want competition to be effective. So you don't want heterogeneity with huge amounts of dispersion in there, but you don't want complete homogeneity because you want some kind of competition. So these kinds of results speak that first of all, the first answer is, well, life is not as simple. It's not just a matter of putting a few really brilliant minds in a classroom and you're going to raise everybody. But on the other hand, it does say that we can, that some kind of tracking, some kind of reorganization of the classroom can be important. Now, let me just take you very quickly through the model. Test scores depend on own effort and peer ability. This is important because one of my themes is going to be how does this link with the empirical model. Preferences depend on test score outcomes, and effort is expended in obtaining them, and importantly on class rank. Now, so you have a utility function that kind of looks like this. This is arbitrary, so which is very good, of course. You've got here achievement of the individual student, and you've got a kind of cost of effort here, endogenous cost of effort. That's kind of a choice variable. And then you've got the rank concern, but it's kind of shifted away from zero. That's something that needs to be estimated somehow. And then all this is solved out as a function of effort, and then you can maximize this. You maximize this, and you get the equilibrium level of effort for each student given equilibrium in the classroom. Okay, so that's all very clever and nice. It relates to other things in the literature. Now, one question I had, I didn't manage to work it out, but it's not clear to me, whether this multiplicative structure here in the rank itself is restrictive or not. It sounds to me quite restrictive because it's a bit like an expected utility framework. So it's almost like imposing a cardinalization there. A little bit more understanding there, because there's a lot of emphasis in the paper how non-parametric it is, but this is not a particularly non-parametric aspect. So I'm not sure how much the comparative statics depend on this. Now, the implication of the model are rich and interesting, and we kind of heard of them. The important thing is that if the density is high around you, this induces more effort. since it's easier to overtake people. So basically, the variance matters in the sense that a little bit of variance means that if we start competing, there's some hope of overtaking other people, so there's an incentive induced, right? So that's the key idea. But of course, if I'm going to have to overtake some kind of genius in the classroom, I just won't bother. So that's the kind of mechanism that's being analyzed. Okay, so now, at a more general level, this is a bit of a normative slide till I get to the empirics. At a more general level, it would be nice to know the production function in the classroom. Is it really the case that teachers want students to compete that much? Perhaps they don't want to do that. Perhaps they fight against competition and they would like a bit more cooperation. So at some different level, we're taking it as given that students might care about rank. They might, but at the same time, teachers might prevent competition, and they might want to induce cooperation. And perhaps they do that because they know the production function. They say that if they're everybody at each other's throats, perhaps it's not so productive. Perhaps it might be, cooperation has its advantages, I think. So the empirics are basically written like this. We write achievement, which is a test score, as some kind of function of cost of effort. Now, there are two key points in the paper which I'd like to question. First of all, so the idea is that we're going to do diff and diffs, right? But we're going to do matching diff and diffs. We're going to take kids that have the same C, right? We're going to match them, and then we're going to do diff and diffs there, right? But that, of course, implies that we have to assume that C is completely observable, or up to a set of parameters. It can be, basically, it's a kind of a propensity score idea. However, I think that's a bit of an assumption that's of a stretch. The other thing is that this specification here doesn't seem to me totally consistent with the underlying model that motivated the theory, where you have, where the production function for test scores depends on effort, depends on average ability in the classroom, not performance, ability, plus an additive bit. So this is inherently non-separable, and I can't see how I can take this from here to here, because this is just the rank, right? This is not consistent with that. The other issue that I'm a bit concerned about is that if I was thinking of this model econometrically directly, I would think that there are unobservable classroom characteristics. For example, I don't really observe the average ability in the classroom. So I would like to think of mu here as unobservable, right? And so I have an unobservable there, I've got an unobservable there, got an unobservable there, and I think I should have an unobservable there as well. So then the big question is, can I really fit this into a diff and diffs framework? And that's my problem. So I'd have to skip a little bit. So let's go to the fundamental structure of a diff and diffs problem. The fundamental structure of diff and diffs problem is defined in Altongian Blanc and in Athe and Imbens and probably elsewhere, but that's the two references I've got in my mind at the moment. So I've got the counterfactual, I've got the y here, and I'll think of this as the counterfactual test score. And the way, in order to be able to do diff and diffs, the generic assumption is that I can write this as a monotonic transformation of one unobservable, which has a time invariant distribution and a time effect, say. Okay, now, so in other words, if I go back to the theoretical model, I have to ask myself, can I write this as a monotonic transformation, the counterfactual, not the treatment world, can I write this as a monotonic transformation of one unobservable and the time effect? And I can't see how I can do that. Or I can't see why I can do that unless I make the assumptions that are made in the empirical model, which basically remove the interaction with the classroom unobservable and what I think should be also an individual level unobservable, and imposes this additive separability structure. Now, don't forget that the key point about this, the empirical structure of the paper here, is that we're trying to get at the effect of the variance, but we never actually observe the variance. So we observe things that will shift the variance if we match these things up. So this kind of a comment here, can be important as far as this is concerned. Now there's another related comment that has to do with diff and diffs in general when we are dealing with test scores or other variables, outcome variables that don't have a natural scale. Okay, so test scores, whatever monotonic transformation you take of a test score, it conveys exactly the same information. So I can take logs, I can take exponentials, I can take whatever, so long as it's strictly monotonic, it conveys exactly the same information. Now, the problem is that if I then take an arbitrary scale and then I do a diff and diffs, I do not have, I do not necessarily preserve the effect that I would get with any other transformation. What does this say? It goes back to this point here, that this h function here is not known, right? It's fundamentally not known when we have to do with test scores. Perhaps with dollars, we might say, okay, this is dollars, and then I assume that, and I have an additive separability suitable for diff and diffs with dollars. But when I have test scores, basically, since I can, if you give me a linear function there, then I can say, well, why that and not any other monotonic transformation? That automatically implies that, that I cannot assume additive separability, even if the model is kind of separable, because the left-hand side is subject to the monotonic transformation. So my conclusion of this is that I was actually really impressed by both the motivation of the model and by the idea of the way that the earthquake is used. There's a lot of work in corroborating some of the underlying assumptions on the empirical variation and so on, and the exogeneity. What I think the paper needs is there's too many slides. What the paper I think needs is a stronger link between the theory and the empirics. And yes, because this paper lives off the theory. I don't think it makes sense to do a diff and diffs without the theory. I think Michela is right to put the theory down and say, this is what I'm identifying, because you're trying to identify a very subtle effect, mean preserving risks in the classroom. So this has to live off the theory. So as a result, the link between the theoretical model, as it's implied, and the empirical model, and the clarity on the assumptions that you need to go from one to the other, I think is central. Of course, I recommend you read the paper. It's a very creative paper. It's got a lot in it. It'll take you a bit of time. It's not bedtime reading. But yeah, it's a nice thing.